now that we have some comfort level with writing out sequences given a rule, or finding the next terms in a sequence given a few terms already establishing a pattern, now what we want to do is try to figure out, once we see that pattern in the sequence, how can we write a direct rule for the nth term of the sequence. Now, it's important to understand when the directions ask you for a direct rule, that does not mean a rule using the previous term. When you look at this sequence here, as the one we did in the last video, we noticed that each one of these was 5 apart from the other. So we have something that's called a recurrence relation, where you would say let the first term be 4, and then let the next term be the previous term plus 5. That's a recurrence relation. There's lots of applications for that. It's certainly discussed in this chapter, and we can solve certain problems like this. But we did talk about, what if I wanted to jump to the 93rd term in this sequence? Well, if I want to find a sub 93, I have to find a sub 92 and add 5. Well, how do I find a sub 92? I have to find a sub 91. And that means I have to find all these previous values just to get to this one spot. That's not a direct rule. For the direct rule, what we need to do is to be able to jump straight from n to the nth term in the sequence. Okay? So let's take a closer look at what's going on. We're adding 5, we're adding 5, we're adding 5, we're adding 5. What happens if we continue to add 5? Every time we repeat addition, that's really multiplication, right? To get to this 4th term in the sequence, we had to add 3 5s, right? To get to the next term, the 5th term in the sequence, we would have to add 4 5s. What are we adding 4 5s to, or 3 5s to? The initial term 4. Okay? So the next term comes from adding a bunch of 5s. When we add a bunch of 5s, we can really multiply by 5. What we can do to write a rule for the nth term is to say a sub n equals 4 plus 5 times n minus 1. Okay? The reason we're using the n minus 1 here is the a sub 2 came from adding 1 5. Right? A sub 3 came from adding 2 5s, and a sub 4 came from adding 3 5s. So we always had one less multiple of 5 than the number we were looking at. That's why we have this n minus 1 that's over here. Now let's test it out to see that this rule works. A sub 1 would equal 4 plus 5 times 1 minus 1, which would be 4 plus 0, which would equal 4. A sub 2 equals 4 plus 5 times 2 minus 1, which would equal 4 plus 5, which would equal 9. A sub 3 is 4 plus 5 times 3 minus 1, which would be 4 plus 10, which would be 14. A sub 4 equals 4 plus 5 times 4 minus 1, that's 4 plus 15, which would equal 19. And we should feel pretty confident that we do in fact have the right rule here. So what are the components of this rule? This 5 that's right here, that's our common difference, d. And this 4, right, is our first term. So it should be pretty easy to replicate this pattern. Anytime you see a common difference, right, you know that that difference is going to get multiplied n minus 1 times and then added to the first term. Okay? Now let's see if we can use a similar line of reasoning for the second one. For the second one, remember we're multiplying by negative 2, we're multiplying by negative 2, we're multiplying by negative 2, we're multiplying by negative 2. If repeated addition is multiplication, what's repeated multiplication? Well, if you multiply by 2, multiply by 2, multiply by 2, you're dealing with the powers of 2. Now in this case it's negative 2. So our a sub n, we're going to start with the first term, and then we're going to multiply negative 2 to the n minus 1. Again, we're using the n minus 1 part of this here because to get to a sub 2, right, we just use one negative 2. To get to a sub 3, we use 2 multiplications of negative 2. And to get to a sub 4, we use 3 multiplications of negative 2. So we're using one less then the amount. Now the -3, again, that's our first term, and this -2 here is our ratio. Okay, I'll just test the first two terms here just so we can see that it works, or maybe the first three. A sub 1 would be -3 times -2 to the 1 minus 1. That's -3 times -2 to the 0, right, which is just -3. Now a sub 2 will be -3, -2 to the 2 minus 1, which will be -3 times -2 to the first, which is +6. A sub 3 would be -3 times -2 to the 3 minus 1, which would be -3 times -2 squared. That's 4 times -3, which is -12. Okay? So this rule works as well, and again, this can be generalized. Anytime you see a geometric sequence like this, you know you're going to multiply that first term by successive powers of the ratio, always using the n minus 1. Okay? Now this last rule, right, there was no common difference or ratio. We just had to recognize that when n equals 1, we had 1 squared. When n equals 2, we had 2 squared. When n equals 3, we had 3 squared. When n equals 4, we had 4 squared. So the nth term is going to simply be n squared. Okay? So you might see some versions of sequences that are similar to n squared. You might see common differences, common ratios. I wanted to go through a couple more examples for you right here. Same basic structure. Let's see if we can recognize the pattern. This first one, I'm going to subtract 7, then I'm going to subtract 7, subtract 7, subtract 7. So I've got repeated subtractions of 7, repeated subtractions, repeated additions. Those are all multiplications. So the way you're going to write the nth rule, it's a common difference. So you're going to start with the 23, and you're going to, instead of adding multiples of 7, you're going to subtract n minus 1 multiples of 7. Okay? To get the second term, over here I used one multiple of -7 to get to the third term. I used 2 multiples of -7, and so on. Okay? For this next example, I'm multiplying by a half, multiplying by a half, multiplying by a half. So the nth term will be the first term times powers of a half, again using n minus 1. Once you've seen a few of these, it becomes pretty easy to replicate. Now this last one, I don't see a common difference or a common ratio. The difference is 3, 5, 7, 9, and so on. There's no common ratios here. Sometimes it helps to write out some familiar patterns, like in our case, the perfect squares, and then you might see some connection. The difference here is 3, the difference here is 3, the difference here is 3, the difference here is 3. This is supposed to be a 16. It's a little hard to write that. The difference here is a 3. Okay? So we know what this sequence is, 1, 4, 9, 16, 25. That's the sequence. The nth term of that sequence is n squared. How do you think we're going to get here? Well, we have to go up by 3. So for this one, sort of more by observation. If you don't see the perfect squares, maybe you would try the perfect cubes, or just try some other basic sequence. These are the most predictable ones that we should expect you to be able to do because they follow a nice pattern. They're easy to recognize, and the formula kind of works itself out once you've seen it a few times. These you have to do a little bit more exploration and kind of maybe get a little more creative. Okay? So it's important that you practice these. We really want to focus on the direct rule so that we don't have to calculate all the previous terms to get the next one.